Now we can use these expressions that we have developed to find rates of different quantities. For example, rate of change of E is quite easy. So E, remember, is half F transpose F minus I. Take E dot, it will give you F transpose dot plus, that's right, it's empty. E dot is half F transpose dot F plus F transpose F dot. F dot is LF, so F dot transpose is so F dot is LF, F dot transpose is F transpose L transpose. So this is F transpose L transpose F, and this is F transpose L F. We can take F transpose and F common, so we have F transpose L transpose plus L times F. So half L transpose plus L is the symmetric part of L, and that we have called D. So this is equal to F transpose dF, another important relation. So E dot is equal to F transpose dF. That is something we need to remember. We'll use it in the future quite a few times. Now we can do other rates as well. For example, we can do the rate of change of a line segment. So dx dot, so dx is f times d capital X. D capital X is not a function of time, so dx dot is f dot dx. F dot is LF, so but f dx is again d small x, so this is, so the rate of change of a line segment dx is related to the line segment itself through L. So that's another important relation, that dx dot, the rate of change of a line segment, is related to the line segment through L. Similarly, we can use the Nansen's relation to find the rate of change of a surface element in the deformed configuration ds dot. Remember, ds dot is n times d, the scalar area S, and that is related through the Nansen's relation to the corresponding scalar area capital N d capital S, which we had called d capital S vector in the undeformed configuration. So if you now want ds dot, you have j dot f minus transpose plus j f minus transpose dot times d capital S. D capital S is obviously not a function of time. J dot, from a previous derivation that we have done, we know J dot is J trace of L. Trace of L, remember L is split into a symmetric part D and an antisymmetric part W. Trace of L is the same as trace of D because the trace of W is 0. So this is J trace D F minus transpose plus J F dot minus transpose. So that is easily found from F inverse equal to I. So F dot F inverse plus F inverse dot is 0, which means F inverse dot is minus F dot F inverse times F inverse. Yeah, I think this is right. So this is minus F inverse L f f inverse, because remember f dot is LF, so f inverse is I, this is minus f inverse L. Now I want to take the transpose of this because I need f inverse transpose dot. So if I take the transpose of this, f minus t dot is equal to minus L transpose f minus transpose. So here I'll replace it with minus L f minus transpose L transpose f minus transpose d capital S. So J f minus transpose d capital S is d small s. J f inverse transpose d capital S is again d small s. So this becomes J trace d times identity minus L transpose times d small s. Again, we have related the rate of change of a a small area segment d small s to the area segment itself. Here also we could relate the rate of change of a small line segment to the line segment itself through this L, and here ds dot has been related to ds through this tensor. Okay, so now we will do a problem which has a little bit of finite element in it. So these are configurations of a four-noded element as 1 second apart. So it goes from 1 to 2, 2 to 3, 3 to 4, and all this happens in 5 seconds. And each of these are 1 second apart, and then in this 1 second we assume that the morphing from 1 to 2 takes place in a linear manner. So let's try to write the motion between 1 and 2, then we'll write it between 2 and 3 and so on. So first write it between 1 and 2, which is obviously a simple shear, and at the end of the simple shear it has tilted by an amount A. So this would be the motion at time t equal to 0, small x is equal to capital X, of course, and at time t equal to 1, small x is equal to x plus at times y, and y is equal to capital Y. So once you have the motion, this is between configurations 1 and 2. So once you have this motion, it's easy to calculate the f. Once you get f, you get f inverse, and f dot is just the time derivative of it. So when you take f dot, you get 0 here, a here, 0 here, 0 here. So this is your f dot, and f dot is L. L is f dot f inverse. So this is your L. Once you get L, L plus L transpose, half of that gives you the rate of stretch, and that is this. So the rate of stretch shows this is the rate of stretch for an element, a square element, one by one, undergoing simple shear. Now from 2 to 3 in 1 second, this stays tilted by A but grows in the y direction by B. So at the end of 1 second, it would have grown by B, whereas x's would remain the same. X's would remain as they were in 2, but they would grow in the y direction by B. So the motion would be something like this. The x's were capital X plus ay, which was at the end of this time step at t equal to 1, and the y the small y would be 1 plus bt into y, because at t equal to 0, y is equal to y as it was at the end of this motion, and at time t equal to 1, small y would be 1 plus b into y. Again, do the same thing. F is easy to calculate, f inverse, f dot, L and D. Just follow. from 3 to 4, from 3 to 4, it is again a simple shear, but in the other direction. So it's tilted here by A, but from 3 to 4 it becomes straight again. So it untilts itself, uh, which means that so y doesn't get affected. So at the end of this time step, y is 1 plus b into capital Y, so it remains at that, and x untilts, so capital X, and this is like a simple shear, except that at time t equal to 0 it is x plus ay, what it was at the end of this time step, uh, but at t equal to 1 it is back to capital X. So this is the untilting simple shear. Again, we do the same thing. These are easy steps. F inverse F dot and L, then symmetric part of L gives you D. Finally, we have the element coming back to its initial configuration by compressing this by an amount b. So at the beginning of the time step, from 4 to 5, it was at 1 plus by. So at the end of the time step, it is 1 plus by minus bt. So at t equal to 1, this is equal to capital Y. At t equal to 0, it is 1 plus b, and x remains at capital X. And again, you see that you get a symmetric L in this case, so that your D is equal to L. So this is the way it's done in finite elements. Gives you an idea of how it's done in finite elements.